All right, now we're going to move into chapter 8. It deals with vapor power cycles. And you might think, wow, where do we see vapor power cycles? We see them in a lot of places, but we especially see them in the generation of electricity. And everybody in this room consumes electricity. You have since you were probably born. I don't know if anybody was born in a place where there's no electricity. Okay, I think everybody's there. Maybe 100 years ago, for sure, there were some people born in places there were no electricity. But here's a power plant that's owned by you, the ratepayer, the citizen of the city of San Antonio, because we have a municipally owned utility here in San Antonio, CPS Energy. It's owned by the citizens of San Antonio through the city of San Antonio government. It's supervised, run by the city council and all that. So anyway, it's down by Lake Calaveras. Maybe you're a fisherman. Maybe you've been down there fishing on that lake. Maybe you've seen these power plants. But this is a very large coal-fired power plant. So we don't have an abundance of coal in the vicinity of San Antonio. We actually bring it in by railroad cars, whole train loads. Maybe you've seen them somewhere coming in to San Antonio. We usually get about a train load and a half per day, I think, per power plant. That's a lot of coal coming from Wyoming, the state of Wyoming. That's where we get our coal, low sulfur, good coal. Anyway, we burn a lot of coal to generate electricity. How else do you get electricity? You're a consumer of electricity. How do you get it? Where does it come from? Especially if you're purchasing it from CPS Energy. A lot of it's made by coal. How else? There's almost zero hydro in San Antonio. If you're in Tennessee, there's a lot of hydro. Your state of Washington, there's a lot of hydro. But there's a lot of nuclear. Did you know about 30% of the electricity to 40% of the electricity consumed in San Antonio last year and the year before and last many years running now has been generated using a nuclear power plant? Where's a nuclear power plant that's generating electricity we're consuming in San Antonio? Bay City. There's 2 units. For a while, they're proposing to grow it to 3 and 4 units, and then that got squashed by the city council, especially, okay, through some input from the citizens and debates, etc. There's another couple of units somewhere in the state of Texas. They're not owned by CPS Energy, or CPS Energy doesn't own a part of it. The CPS Energy owns a part of the ones in Bay City. Anybody from up in the Fort Worth area? Yeah. Comanche Peak? Comanche Peak. They have 2 units up there. They've also proposed to build additional units. They have the lake capacity there, the site capacity there, but nobody's touched expanding nuclear power in the United States for quite a while. But probably some of you may end up in that industry. I know some grads from UTSA, both electrical as well as mechanical. I don't know any civils who are in this industry, in the nuclear power plant industry. Okay. How else is some of the electricity generated here? Wind. Now, wind doesn't use a vapor power cycle. Coal and nuclear both use a vapor power cycle, but the wind, natural gas, solar, they do not. And so there are some fractions. This wind fraction is growing. The solar is modest, small, but still growing. And natural gas, CPS, is really trying to grow it. That's the gas power cycle's next chapter. How they generate electricity by burning natural gas. Used to be, and there's probably still some plants that burn natural gas just like they burn coal to make electricity. Feed it into a vapor power cycle, but not very efficient. You could use natural gas in a gas power cycle. So when you think about generating electricity, you usually burn something or fission. In the nuclear power plant, it's controlled fissioning. Fissioning just like in a bomb, nuclear weapon? Yes. But nuclear weapons also use fusion. Those are higher tonnage, higher yields. But let's not get down there. But that's, yeah, it's controlled for peaceful purposes, for good purposes, make electricity. In the United States, used to be a real leader, but I think it's still hovering around 20% of the electricity generated in the United States is generated by nuclear means, where if you go to France, it's 90+%. I can't remember the exact numbers.
Why are we shying away from expanding?
Oh, well, that's political, and people are very frightened of it. And since 3 Mile Island, there you go. So it goes back to a lot of things. But in France, it's huge fraction. You go to China, they're building a lot of nuclear power plants, as well as coal-fired. And if you go to India, I think they're building quite a few. I think Pakistan has quite a few. I think some other countries are growing the proportion of nuclear power. I think Japan as well, but I'm not certain on all of them. It really depends on the mood of the people in the country, and they say, like, no, we don't want that, or yes, we want it. So, but these boil water, make steam, pass it through a steam turbine, and now let's move on and study this. So we're going to talk about the Carnot vapor power cycle, and then we're going to talk about the Rankine vapor power cycle. So I thought I'd spend a minute talking about this person whose name is still kicked around. So Nicolas Léonard Sadi Carnot was in France. These are the years that he lived. So he lived at the early part of the Industrial Revolution, and you could do the math from the year he was born to the year he died, and guess what? That's sobering news for all of us, isn't it? He only lived to be 36 years old. But he did something when he was around, I think the math shows me he was around 28 years old, that we still can talk about today. He wrote a book, and it was titled in French, so they have to translate to English, but the translation in English is something like Reflections on the Motive Power of Fire. Thinking about reflections, thinking about how I can burn something, fire, to produce mechanical power. Very unique. This is really the beginning of the Industrial Revolution. One of the key things in the Industrial Revolution, before it, everything, if you needed to move something, you did it with human muscle or animal muscle. Now, you could actually burn something and it could do work. Now you think today in 2018, you think, that's so straightforward. Of course, no. Only a few hundred years have we had the Industrial Revolution where you could actually burn something to do work, to lift something, push something, transport something, accelerate something. Otherwise, it was all human power, muscle, or animal muscle. Okay. So the key points, which you've studied already in Thermal 1, is that you have this heat engine. It's a device where you bring in some heat, some QH, and you want to convert as much of that to some useful work, but you've got to throw some away. QL, you just have to throw some away. You can't have 100% conversion of heat into work. But that the two temperatures of the reservoirs, the TH where it comes in and the TL, what you reject, they basically dictate the efficiency. And then you say, oh yeah, I remember the thermal efficiency, 1 minus TL over TH. Recall? Yeah, he really had that. And then it doesn't really matter, the second point, it really doesn't matter on the exact nature of the working fluid. And then that's, you say, yeah, I studied the Carnot, but it was ideal gas and a piston cylinder. That's the way it was introduced. You're exactly right. But we could also have water as a working fluid in a Carnot vapor power cycle, or even a refrigerant. It really doesn't matter what the fluid is. It could be ideal gas, could be water, could be refrigerants. So those are the main points. Also, we're going to talk about the Rankine cycle. Now, the Rankine cycle is what, if you want to rename it, you could call it the practical Carnot. It's like some parts of the Carnot are not practical. If you make this change, it's not the exact Carnot cycle, it's the Rankine cycle, but it's very close to the efficiency of the Carnot. Well, it's named after this man who lived in 1820 to 1872. Again, early in the Industrial Revolution. Bad news for me. Look at that. What is this in thermodynamics? People don't live long enough. 52 is not a very old individual. Believe me, I'm past that. Yeah, it's sad. But he grew up in Scotland. He was at the University of Glasgow. He was the Queen Victoria Chair of Civil Engineering and Mechanics, University of Glasgow. In 1859, he produced this book, a manual on steam engines prime movers, etc. You can go to Google Books now and you can read it if you like. He's honored with, yes, that temperature scale, absolute temperature scale in the customary U.S. customary system of units. Some people call it the English system of units, the Rankine temperature scale, as well as some lectures in geomechanics, I think some medal that's given out in this geomechanics area. And then what we here study is the vapor power cycle. So what exactly is the Carnot vapor power cycle? 4 components. Try to memorize them. You're going to have something to bring in the heat called a boiler into the working fluid. Out of the boiler will come some steam. Put the steam through a turbine. That is a device which will drop the pressure and expand the steam and push back blades on a rotating turbine to produce some work out. Work out of the turbine. This was Q into the boiler. Now we want to close the loop. What you have to do is you have to put it through a condenser. That's our third device, where it partially condenses in the Carnot vapor power cycle. When we get to the Rankine, it'll completely condense it, but just partially condense it because we're going to put it into this magical pump, which doesn't exist for the Carnot, which will then compress it and feed it back into the boiler. Okay, so you think, we have a numbering of states. Let's talk about state 1, that's outlet of the boiler, inlet to the turbine, and then state 2, and then state 3, and state 4. So we have 4 components and then 4 states of the steam between the major components. Okay, let's talk about the condition of the steam coming out of the boiler into the turbine. It's saturated vapor. That's what it's assumed to be. And it's going to be at a pressure P1, which is pretty high. And then if we compare, the pressure at 2 is a low pressure. Let's just walk around and figure out our pressures. In our idealized boiler, the goal or purpose of a boiler is like a heat exchanger. It's not to increase or decrease the pressure. It's just to transfer energy by heat transfer into the working fluid. So what about the pressure at 4? How does that compare to the pressure at 1? It's the same. Yeah, it's the same. Likewise, the condenser. We are rejecting heat to the environment, and the pressure has negligible change, so we're going to assume P3 is equal to P2. There's really only 2 pressures in this system, the high pressure and the low pressure. All right. Now we go back to Carnot, and when you brought in heat, you had to bring it in to the working fluid at a constant T high. You can't have some of the heat brought into the water at a low temperature of the water and then some at a high temperature of the water. The temperature of the water needs to be all the same high temperature. This is very tricky. This is where a lot of people, in Thermo 1 get very confused. And I remember you probably struggled with this, or you remember struggling with it. And you say, hold it, I have some fluid, I'm bringing heat in, the temperature has to go up. There's no way the temperature of the steam going through the boiler stays TH. Or can it? How can it? It has to in the Carnot vapor power cycle. How could it come in so the temperature at 4 is TH and the temperature at 1 is TH? How can that be? It's saturated liquid on the inlet and saturated vapor on the outlet. Constant pressure, heat addition, all you did was boil it. So this is saturated liquid on the inlet. This is saturated vapor. If those assumptions are true and you're not changing the pressure, isn't T4 equal to T1? Isn't that the high temperature? Yeah, that's true. So now, also for this turbine, to have a really efficient turbine, do you think that turbine is going to be well insulated? You think that Q dot is equal to 0, or lowercase q, if you want to put it on a per unit mass basis for the turbine, is equal to 0? Sure. We've analyzed turbines enough to think, okay, for a good turbine, to get a lot of work out of that steam that's expanding through it, we're going to have a well-insulated adiabatic expansion, no heat transfer. That would only diminish the performance. And it's going to be reversible. So if you've never studied turbines before, you know, this is a lot to swallow. But you've studied turbines before. So Q is equal to 0. It's well-insulated, adiabatic. And sigma dot is equal to 0. No irreversibility is in that turbine. So what about the exit entropy compared to the inlet entropy? It's isentropic expansion through the turbine. Well, what we're going to do is, in our mind, we're going to say, you know, to really understand this, I'm going to probably plot this on a temperature entropy diagram. Go ahead and put a dome, temperature entropy diagram, put on two lines of constant pressure. A high pressure line, the pressure of the boiler. A low pressure line, a pressure of the condenser. So the high pressure line maybe is up here, like that. How about the low pressure line? Something like this. Okay? Pressure high and pressure low. All right? So, where is state 1? That was the boiler. Out of the boiler, high pressure, saturated vapor. Where would that be on this TS diagram? Right there. Right? Where is state 2? We just talked about it going to a low pressure, and it's reversible adiabatic isentropic expansion straight down. There's state 2. Okay, to get to state 3 is the hardest one to get to on the Carnot vapor power cycle. State 4 is a lot easier to find on this diagram. Where is state 4? High pressure, saturated, the other corner, right? High pressure, saturated liquid. If that's state 4, and you think about this pump, and that pump is well insulated, and it's going to be reversible, sigma dot's equal to 0, no entropy generation. What's the relationship between S3 and S4? They're the same. Ah, that's the clue to finding where state 3 is. Otherwise, state 3 is hard to find. You got to think about, 4, I know where that is. And then there's a special pump that is going to take some two-phase mixture, inlet, and boost the pressure from low pressure to high pressure. So this is what the Carnot looks like. Hey, when you had the other Carnot vapor power cycle, or a Carnot cycle on a TS diagram, wasn't it always a rectangle? Yeah, it's always a rectangle. All of the heat comes in at TH. All of the heat goes out at TL. This is, sometimes you draw it like this. This is the work out in the turbine from 1 to 2. This, sometimes you draw it like this, Q out in the condenser. This is some work in with the pump, and this is some Q in the boiler. All right. Well, if you got that, you're well on your way to solving some problems. So I'm going to revisit some of this aspects before again, but there's two metrics that are key to when you have a power cycle. One is the thermal efficiency. The thermal efficiency. What was our thermal efficiency of the cycle? What was that? You're going to find numerically that you'll be able to have 1 minus TL over TH, and that's going to work. But here what I'm going to do is I'm going to say I'm going to take some net work out of the cycle, and I'm going to divide it by what is the heat that I had to pay for to bring into the cycle, which is to feed the boiler. Dumping heat in the condenser to the environment is not currently taxed. I'm not saying it won't be taxed in the future. Thermal pollution, I mean, they're going to tax carbon dioxide emissions. That's going to be taxed sometime in the future. It will. You just can't, exhaust carbon dioxide out there into the environment. They'll be taxed. In the future, my guess is that'll happen. But there's probably not going to be a heat rejection tax or penalty. You can just dump heat to the environment. Okay, so go outside and blow off all the hot air you want. All right, now that's one metric. The other is BWR, back work ratio. Back work ratio. Back work ratio was, look at 100% of what comes out of the turbine, some of it has to feed back to drive the pump. So we'll put it W back to drive the pump. What goes back to drive the pump? Now, as I've written it, this is always going to be confusing to students. I like to work with things that are positive, and I know the direction. Like, I know the heat is out of the condenser. It's out of the condenser to the surroundings. But if you do the general control volume, you're just beginning to study it, what's our assumed direction for any control volume when we write the first law? Q in is positive. So sometimes I'll put a negative sign on this so that because WP is a negative term, and I want to make it a positive back work ratio. All right, so let me do this. Let's spend a little time and go around each component and have a review of Thermo 1. So this is the boiler. What did I put in here for a little dashed line? A CV, a control volume. It cuts outlet state 1, cuts inlet state 4, and is there any W dot out of the boiler? No, that's zero. There's no shaft power in or out of boilers, or likewise condensers. They're just heat exchangers. What did we write right here? What is this equation right here? First law, conservation of energy. It's our most general. So what we do is we write it for this control volume, and then we say, is this operating in steady state? If it is, what's that term equal to on the left-hand side? 0. If you neglect changes in kinetic energy, and you neglect changes in potential energy, these terms cancel. They're 0. If you have steady state, you have the mass flow coming in is equal to the mass flow going out. And we just have one m dot. Then you can rewrite this as just the mass flow rate times the enthalpy coming in is H4, and the enthalpy exiting is H1. True? Okay. What about this work term? I already talked about that. That's 0. The power, there's no mechanical power out. So we have 0 is equal to Q dot into the control volume. This is into the boiler, plus the mass flow rate through the boiler times H4, the inlet, minus H1, the exit enthalpy. I pause. Did we follow that transition of the general equation to this problem for this control volume for this boiler? Thumbs up. Then what we do is we put Q dot boiler divided by m dot of the mass flow through the boiler is equal to H1 minus H4. Did I do that math right? And then what is the name calling of lowercase qb, with or without the dot? Lowercase qb is equal to Q dot b divided by m dot through the boiler. True or false? That's true. So this is like a specific heat transfer. What are the units on this term? Kilojoules per kilogram. What are the units on Q dot? Kilojoules per second. What are the units on m dot? kilogram per second. So you see the per seconds cancel, and the world is good. Life is good, right? This is all consistent. So I will very quickly sometimes write this equation, and students go, where did that come from? I was getting a lot of this at the 8:30, so I spent some more time here. Okay? You need to do it. This is Thermo 1 review, but I just did a good review for you, okay? Guess what we do next? Oops. All right, what happened? I lost on my thing. Guess what we move to next? The turbine. You have to do it for each component. You have to get these equations correct. So for the turbine, steady state, is there any heat transfer? No. Q dot for the turbine is 0. We have a well-insulated turbine. We neglect changes kinetic potential, 1 mass flow rate in, 1 mass flow rate out. So we have 0 is equal to the W dot out of the turbine plus the mass flow rate coming in at H1 minus H2. You have W dot turbine divided by M dot equal to H2 minus, sorry, right there. Even I don't go, there you go. Right? I dropped off that negative sign. And so this is the lowercase w subscript t. That's equal to the change in the enthalpy. It comes in higher enthalpy, goes out lower enthalpy. What is lowercase q for the turbine? Well, that would be q dot into the turbine divided by the mass flow rate through the turbine. It's 0. It's 0, isn't it? All right, let's press forward. What about the condenser? This is where, what is the direction for that Q? What we're going to do is we're going to put QC as positive into the condenser. Okay, so it's steady state, no work or power, no negligible changes here and there. So we'll get that 0 is equal to Q dot into the condenser plus the mass flow rate coming in H2 minus H3 going out. So Q dot C divided by M dot is equal to H3 minus H2. Look good? So lowercase q sub C is H3 minus H2. That by nature is going to be negative. I like to personally avoid negative terms in my calculations, but this is one of the times I think early on, let's just stay with the sign convention, and we know that it's not, it's a condenser. The heat is transferred out. But if we stay with our sign convention, we'll have a negative QC. So it'll be a lower enthalpy. H3 will be lower than H2. And minus a higher enthalpy, this will be a negative term. Likewise, we go to the pump. Same equation. We have no heat transfer, steady state. These terms drop. So we're left with 0 is equal to minus W dot out of the pump plus the mass flow rate in enthalpy 3 minus the mass flow rate out times enthalpy 4. So we have the W dot divided by M dot P equal to H4 minus H3. So the specific work of the pump, oh man, I left that negative sign again. You can tell I don't like having the negative signs. It's hard for me to stay with the sign convention, but I'll just have to do that to help you. So this exit enthalpy is greater than the inlet enthalpy, hence you get a negative term. Somebody says, I remember studying pumps, and there was this simple equation. The specific work of the pump is approximately V of the inlet fluid, if it's saturated liquid, if it's liquid going into the pump, times The P4 minus the P3. Yeah, that's true. And if you wanted, you put a negative sign on it. But this is getting a little ahead of ourselves. We'll review that. But does anybody remember that equation? It's only good. It's at the end of chapter 6. It's only good if V is constant through the pump. And that would be if it's a liquid. Liquids are incompressible. So you're given a problem like this. So the water is a working fluid in a Carnot vapor power cycle. The boiler is at the 8 megapascal and the condenser is at 20 kilopascal, and you're asked to calculate things like what is the work developed by the turbine in units of kilojoules per kilogram. So that's W sub T, and then how about the pump? W sub P. 2 answers for part A. And then the heat transfer in the boiler and condenser, lowercase qb and lowercase qc for the answers for part B. Then the backwork ratio and the thermal efficiency. These are traditional things to be solved for. How do you approach solving this problem? Step 1, this seems almost too simple. Get a schematic. Of what? Of the 4 components. And label the states. Isn't that already done in the textbook? Great, be consistent with it. But if you go to a different textbook, maybe state 1 is the inlet to the boiler and not state 1 being the outlet from the boiler. So you would have your 4 components and your 4 states. What's the next thing you do? Well, I would say get a property diagram to help you. Which property diagram? Probably a temperature entropy. You could get other property diagrams. How about for the third thing? I would get a table of all pertinent property values. And we already know the key property values are the enthalpies at those states. I really need to get the H's. I'll need the S's to help get the H's. So the property values are the pressure, temperature, quality, enthalpy, entropy. At what state? State 1, state 2, state 3, state 4. Get a table of all your property values, and the key ones are going to be the enthalpies at state 1, 2, 3, and 4. The next thing to do is get another table of all of your energy transfers. The energy transfers are the Q's, the energy transfer by heat, as well as the W's, the energy transfers by work. And this would be for each of the 4 components. So I would put the 4 components: boiler, turbine. I'm running out of room. Let me scroll down a little bit. So it would be boiler, turbine, condenser, pump, and you'd say, okay, the Q and the W, and I'm going to try to stay with the sign convention, and then you'd say, well, this is the Q into the boiler, and then this would be the work done by the boiler. One of those 2 is 0. Yeah, so you could even put a 0 right away. And then you say for the turbine, hey, that was insulated, but I need to calculate the work of the turbine. The condenser, Q of the C, 0. So anyway, there's 8 possible entities, but 4 of them are 0 values. Okay? But once you have all of these, what you could do is, if I sum all of the work column, what does that equal to? The net work. If I sum all of the Q's, what does that equal to? Q net. For my problem, is the Q net equal to the work net? Absolutely must be. That's a good place to check your work. If it's not, look for your error. These must be the same. All right? And then the last thing is the last parts. It basically calculate the metrics. And those are, you could put them in a table. You don't need to put them in a table, but what is the back work ratio, and then what is the thermal efficiency? And the thermal efficiency is the ratio of this work net divided by the Q of the boiler. Pieces of information that are already organized in your table. And in the back work ratio, it's going to be here I'm going to put the negative in front of the work on the pump because it's negative as the way I've written it. And then divided by the work out of the turbine. The information that you have already put into your tables to calculate the metrics. And the problem's solved. Okay? So, you created a schematic of what? Yeah, make a sketch of the components and label your states. You say that's pretty trivial. I would also put in the property diagram, the temperature, entropy, put your states on the property diagram. That's a bad looking dome. Anyway, it looks like an A, doesn't it? Property diagram. Then you create a table of property values. The key, pressure, temperature, quality, enthalpy, entropy for this problem. Then create a table of all the energy transfers, the work and the heat transfers. Of these 8 entities, 4 are 0, and you're going to be interested in the summing of all the Q's and the summing of all the works. And then the metrics, 2 of them for sure, back work ratio, thermal efficiency. Does that overview help? How many people remember doing Thermo 1 problems like this? Yeah, you did, right? All right. So here is the solution to that problem. Okay. We had 8,000 kilopascal, which is 8 megapascal. P1 and P4 are the same. P2 and P3 are the same. I'm going to put it on a property diagram. Maybe I should have done that. Yeah, here it is. Let's show it on a property diagram. This is drawn to scale using some very, very reliable software, RefProp, which students can download the version for free, and you can reproduce this plot if you have the time and interest. And so here is a temperature entropy. And what do we have? 8 megapascal is our high pressure. So right here is state 1. And right here is state 4. This is saturated liquid, saturated vapor. When you expand down to 20 kilopascal, it ends up being a quality 75% or less. And then that's state 2. State 3, you stop the condensation and put it through that special pump at a quality looks like around 30% quality. So there's the property diagram. All right. So let's jump back, take a look at some of the numbers. Around 70% for the quality at state 2. Around 34% for the quality at state 3. This is saturated vapor, saturated liquid. There's my S's. They're the same. S's are the same. These are the key properties, the enthalpies. A lot of work to get them, but once you get them, you can calculate the turbine work out, positive. Pump, it's shown to be negative. The work into the boiler and the heat transfer into the boiler and then the heat transfer into the condenser, which is negative. We sum these two columns, so Q net's equal to work net. And then here are our efficiencies. And notice, this number of 41.4% is calculated going through all the tables and interpolating and getting those enthalpies and using them. And if you use the very simple equation that the Carnot efficiency should be 1 minus the low temperature over the high temperature, you get the same number to at least 3 significant digits, which is startling. Because it's like, I went all this through the equations and appendices with the quality, and yet I get the simple equation gives me the thermal efficiency. Yeah, it's It's pretty neat. It's all consistent. All right, I should spend a little bit of time talking about 20 kilopascal. So, with this 20 kilopascal, if I look at the steam going through the condenser, is that in a state of vacuum or is it pressurized? In other words, if somebody comes by and accidentally pokes a hole in my condenser tube, if it's in a state of vacuum, the air on the outside will rush into the condenser. If it's under a state of pressurized, it's not a state of vacuum, then some of the steam will rush out into the room. So we know that the fluid, P2 is equal to P3 is equal to 20 kilopascal. What is the... So if you poke a hole in it, will air rush in or will steam rush out? Which way will it go? Okay, is this pure water inside the condenser? Or is it a mixture of water and air? The working fluid is pure water. The steam tables are for pure water, not a mixture of water and air or anything like that. Okay, if it's at a 20 kilopascal, is that an absolute pressure? I go to my steam tables and I look and I say, oh yeah, there's you look at table A2, A3, etc. There's a lot of pressures in there. Are those absolute pressures or are they relative to atmospheric pressure? Are they gauge or absolute? They're absolute pressures. Okay. So what's unique? What's the air pressure in this room? Roughly 100 kilopascal. Right? Okay. So if the steam is at 20 kilopascal inside the condenser, is it in a state of vacuum? Yeah, compared to this room, it's a state of vacuum. So if a hole inadvertently gets punched in the condenser tube, which way is the flow going to be? Air rushing in. Students, believe me, that's a hard concept. Struggle with it a little bit. Like, how did that system ever... That seems to be impossible, Professor. Where's the vacuum pump? And there's no vacuum pump in this system. Oh, there may be an initial vacuum pump to purge out all the air and then fill it with water, but once it's running, it's good. And a clever engineer knows that no system's perfectly sealed. It may be sealed for a while, but they're going to have some safety features in there which will detect if some air has leaked into my power plant and then every now and then go through a cycle to purge some out, to get some of that nasty air, some non-condensables that may have leaked into my system out. But that's beyond the scope of this class. Here we just assume it's pure steam. Always pure steam. In the Carnot vapor power cycle, the pump is not practical. It's impractical because the working fluid going into the pump, that's state 3, should be all vapor, should be all liquid, should be some liquid and vapor, is too hot or too cold. It really needs to be all liquid. Pumps do not run well on a mixture of liquid and vapor. They have not invented a pump that can take a 33% quality fluid that's at 60 degrees C, pump it out to be, and the 20 kilopascal low pressure, pump it out to be 8 megapascal, and the temperature is around 295 degrees C, and it's saturated liquid. This pump does not exist. Oh, it exists on paper and in theory, but there's not, let's go to Granger and buy a pump and then put it in. It's not going to work. If you want to boost the pressure, that's the primary goal here, from 20 kilopascal to 8,000 kilopascal. You usually use either a pump or a compressor. What's the difference between a pump and a compressor? This may be very obvious to most of us, but you think about it. What's the difference between a pump and a compressor? We see compressors in refrigerant systems, air systems, we see pumps in water systems. And so the compressor is ingesting gases or vapors. Pumps ingest liquids. Okay, one of these are essentially incompressible. Which ones are incompressible? Liquids, they're incompressible. Which ones are very compressible? Gases. And so when you boost the pressure of a gas, the temperature goes sky high. If you boost the pressure of a liquid, does the temperature go sky high? Nope. It stays pretty low, pretty modest temperature change. Maybe a smidgen, but very modest. We'll explore that in this lecture. So now it brings out what they call the practical Carnot cycle or the ideal Rankine cycle. All you do is you leave state 1 alone, you leave state 2 alone, you play with state 3. We need to feed the pump a liquid. So what we're going to do is condense it all the way, and this will now shift to be saturated liquid at state 3. Feed saturated liquid. So what does it look like on our temperature entropy diagram? State 1 doesn't change. Maybe it's 8 megapascal saturated vapor. State 2 doesn't change. It's still 20 kilopascal and high quality. State 3 now doesn't stop here. It goes all the way over. There's state 3. Now, you put it through the pump, and now there's state 4. And this is where it takes a little bit of thinking, but it used to be state 4 was right here. State 4 was saturated liquid feeding the pump. But where is state 4? Here or there? You know, location A or location B? Well, if we have Q dot equal to 0 for the pump and sigma dot equal to 0 for the pump, adiabatic, reversible, what is S4 compared to S3 for the pump? The same. Luckily, we're on a temperature entropy diagram. This is the location of S3. Somewhere along this line of constant S is state 4. Maybe state 4 is up here. Maybe state 4 is here. Maybe state 4 is there. Maybe state 4 is there. Where would state 4 really be? Well, we understand this diagram a little bit better. I'm sorry, I'm asking a lot of questions, really not giving you a lot of time to answer, am I? But what is the highest pressure line shown here? Can you see that this is really a big change in pressure from here to here and then here to here? And so let's say somebody said, I want you to plot 120 megapascal. Where would you think 120 megapascal line would be? You think it would be pretty close to 100 and out there. How about 200 megapascal? It'd be pretty close, but even though you have a range of plots, this out here is kind of no man's land. Nobody goes there. You can't get water there. You can't get water with that low of an entropy and that high of a temperature. I mean, you'd have to get the pressure so high it's not seen on the Earth. Okay? So basically, this is kind of like you just don't get water out in those sequence of states. Oh, you can get a lot of two-phase water. You can get around the critical point water. You can get around ideal gas behavior and supercritical steam. No problems. It's just out in here. It doesn't really exist. So if that helps you a little bit, can you see where state 4 now is? That's the hardest state. It's going to be right there on the TS diagram. So here is a TS diagram. We only put in the 8 megapascal and the 20 megapascal to hopefully clean it up a little bit, easier to see. The circle is where state 1 is. This circle is where state 2 is. This circle is where state 3 is. And state 4 is actually plotted also on this diagram. But to the resolution of the diagram, it's very hard to see, but there's only one circle plotted there, only one circle plotted there, and there's actually two circles plotted so close together. State 4 is so close to state 3 that you have to zoom in. So what we do is we zoom in right in here on the next slide, and there it is. There's actually state 3, and hey, didn't we talk about state 4 being constant S? There's state 4. State 3 is at a point, a line of 20 kilopascal. State 4 is on a line of 8,000 kilopascal. This is drawn with very reputable software to scale. Look at the temperature of state 3. Compare that to the temperature of state 4. Look at 60 degrees, 61 degrees, 62 degrees. What's the difference in the temperature maybe? Half a degree C. Oh, it's a little higher. But it's hard to see on a property diagram. And often you just neglect the temperature difference. But it'll be shown. So we have our schematic. Sometimes they change it with the Rankine. Maybe make the boiler taller, put the pump low. You always put pumps in basements. And actually boilers, if you go visit a coal-fired power plant, they're about 4 or 5 stories tall. They're very tall. Big fireball in there, huge fireball. And so they'll change the schematic, but it's really the same 4 components. And then you'll have your property diagram, state 1, 2, 3, 4. Play around a little bit with state 4 because when you put it through that pump, then you remember from chapter 6, if I take an incompressible substance, I boost the pressure, there's a very simple equation. That's that VDP for the work. Otherwise, I have to interpolate in table A5, if you know what I'm talking about. When I have this constant entropy and I'm boosting the pressure up to 8 megapascal. For this problem, I think I have it on the next slide. Yeah. I'll be looking for compressed liquid. That's the condition of state 4. At 8 megapascal, well, I have a table of 7.5 and 10, so right away I interpolate with respect to pressure. And I'm holding S constant through the pump. It's a double interpolation, and it's not as accurate as just using that VDP. Just use the VDP. I think most times you're reading the book, you say, why don't they just do the accurate interpolation of the data in our table? Well, it's because it's so coarse. It's not very refined. So you get your Q's and your W's. You check that the work net is equal to Q net. Calculate your metrics, backwork ratio, thermal efficiency. You compare it with the Carnot. Remember, we just solved the same problem with the Carnot with the same high pressure and the same low pressure. How come they're not the same? And once we understand why they're not the same, it guides us to improving the performance of the vapor power cycle. So that's what engineers do. They understand the system better, and they're better than the technicians. Sometimes the technicians, they have great insight, but they're limited as to how to improve the system. Hopefully the engineer has the insight of a technician and the experience of a technician, but also the knowledge to understand the system and predict how to change it to make it better. So here's a question that we struggle with. This is a main theme of this chapter. Why did the thermal efficiency go down? All we did was condense it all the way to be saturated liquid right here. Why did it degrade the thermal efficiency so much? Did I introduce irreversibilities in the turbine? Is that it? Now I have a worse operating turbine? No, the turbine's the same. Do I have huge irreversibilities in the pump? No. We had isentropic efficiency in 100%. S3 is equal to S4. I didn't change state 1 at all. It's saturated vapor coming out at that 8 megapascal. Really, state 2 didn't change at all either. but something profound changed. So in summary, our Carnot was a box on a TS. It's not a box on the TS here. T4 is a very, very close to T3. It's almost always grossly exaggerated on a TS diagram that's an illustration like this. I showed it to you to scale with the NIST software. But T4 will be so close to T3, it'd be very confusing to students. Like, T4 is lost. I mean, 0.4, where's state 4? Anyway, we do get a degradation in the thermal efficiency. One thing did greatly improve, though. Look at the backwork ratio. Why did the backwork ratio, we would like a low backwork ratio. Why did that improve so much? Because it's cheap to run a pump. And it's very expensive to run a compressor. And we were having to do a lot of compression of that two-phase mixture going from 3 to 4. So, why is that thermal efficiency, the ideal Rankine, so much lower than the Carnot? Well, I used to use a lot of clickers, so I have these questions recycled. Not using them this semester, but, no, it isn't. They're the same. Both of them have no irreversibilities in the turbines or compressors. That's not true, is it? We just proved that they're different. So, no, that's not right. There are irreversibilities in the turbine. No, the turbine and the pump are reversible. Irreversibilities in the boiler, irreversibilities in the condenser. One of them is the answer. It's in the boiler. All right. You scratch your head and you say, man, it's been a while since I thought about these irreversibilities. And you go back to chapter 6. Did I say there was no shame in going back and reviewing what you already learned, and you maybe have to refresh or dig a little deeper and glean a little bit more? But in chapter 6 or 5, I think they talked about what are the sources of irreversibilities. And I think it helps if you could just memorize them and then recite them. One is friction. And we had the friction with the fluid friction, and that's what happens in turbines and pumps. And it's a catch-all. But it's not just always friction that does it. We have chemical reactions, source of irreversibilities. Later in the semester, we'll get to that, like chapter 13 and 14. But we won't visit that as a topic of irreversibilities, and it's not the one here. Mixing. If I take two things, maybe no chemical reaction, I just take pure oxygen, pure nitrogen, I mix them by opening a valve between the tanks, guess what? Very irreversible. Was that due to friction? No. Due to chemical reaction? No. It was mixing, just mixing. But the one that's important here, that some of you may remember when I mentioned, or maybe it's already in your mind, heat transfer through a finite temperature difference. Whenever you have a finite temperature difference, if I have a wall and it's T1 on this side and T2 on that side, and I have some heat transfer through it, that's irreversible. The only way it can be close to not being irreversible is if T2 is so close to T1 that we talk about an constant temperature difference. I mean, it's the same temperature heat transfer. But then when you study heat transfer, it's like you better, that's like an oxymoron. You need a temperature difference to drive the heat transfer. Or you need an infinitely large area to compensate, or you can be patient and wait an infinitely long time to achieve that heat transfer. But here, what happens to the fluid coming into the pump? It's around 60 degrees C. We analyzed it. We said when it comes out of the pump, what is it around? 60.5 degrees C, right? When it goes into the boiler, the first little couple centimeters into the boiler, what's its temperature? 60 degrees C. I dump some heat into it. Oh, it's finally 61. Oh, it's finally 62. It's finally. It gets up to around 200 and what was it, 95 degrees C. Wasn't that our TH, our boiling saturation temperature at the 8 megapascal? When you're heating it, it's cold fluid. You're bringing in heat from a source that continue to bring it up from 295 saturated liquid to 295 saturated vapor. If it's like your heat source is all at 295, 295 degrees C. Our TH, our heat source, was the same as our working fluid in the Carnot cycle. But right in here, you're doing a lot of heating, not all the heating in the boiler, but a lot of heating in the boiler, just getting it up to the boiling point. That's the section that's highly irreversible. So what we're going to do is we're going to study, this is what we call feed water. What do you mean feed water? It's feeding the boiler. And what we're going to do is we're going to study efficiency to improve the cycle efficiency, which basically introduce feed water heaters. What do you mean feed water heaters? Well, if that's a source of irreversibilities, reduce it to improve the system performance. And what we're going to do is have feed water heaters as one of the mechanisms to improve it. The other thing is we're going to talk about superheating and even go into high pressures, supercritical, other ways of improving the system's performance. But with that, I thank you for your attention. We're all done, and we'll see you next time.